Next topic is the radius ratio effect and coordination number. Radius ratio is an important parameter to predict the coordination number from the relative size of the ions in ionic structure. Ionic solids are made up of cations and anions which have definite arrangements. Each ion is surrounded by a number of ions of opposite charge. For example, in an ionic crystal of the type A positive B negative, A positive ions are surrounded by a definite number of B negative ions. This number is called coordination number of A positive. Similarly, the number of A positive ions which are surrounded by a B negative ion is called coordination number of B negative ion. The arrangement of ions in a crystal, geometric shape, and the coordination number of ions depend on the relative size of the ions or ratio of radii of the ions. The ratio of the radii of positive and negative ions is called radius ratio. Thus, radius ratio is equals to radius of positive ion divided by radius of negative ion, that is equals to r positive divided by r negative. This radius ratio plays a very important role in determining the structures of ionic solids as discussed below. We know that the cations and anions in the ionic compounds are held together by strong electrostatic forces. As a result, the ions try to arrange themselves in a geometrical arrangement in which the attractions between the opposite charges are maximum and the repulsion between the similar charges are minimum. Consider, for example, an ionic crystal in which a cation A positive shown by a dark circle is surrounded by octahedrally by 6 anions, B negative shown by hollow circles. Only 4 B negative ions are shown for simplicity. There will be 2 more B negative ions, one above and the other below the A positive ion, but these have been omitted for the sake of clarity. The most stable arrangement is one in which the anions are touching each other and the cations simultaneously. In this case, the attractions will be maximum and the repulsion will be minimum. Such a structure will be quite stable. However, if the size of anions is less, cations same, the anions will no longer touch other anions and the structure will be unstable. Similarly, if the size of anions is large, cations same, all the anions will not be able to touch the cation simultaneously. This structure will also be unstable. Let us consider as to how the change in radius ratio r positive divided by r negative changes the structure of the compound. Consider the stable structure in which all the anions are touching each other and the cation simultaneously. Octahedral arrangement, but only 4 are shown for clarity. Now, if we decrease the radius ratio either by decreasing the size of the cation or by increasing the size of the anion, then the structure will become unstable. All the anions will not be able to touch simultaneously the cation. In order to touch the cation, the anion have to go closer and closer, and therefore repulsion will increase. When the radius ratio is further decreased, a stage will reach when one or more anions may be pushed away so that the remaining anions fit around the cation, giving more stable structure. In other words, there may be change in coordination number from 6 to 4. Alternatively, if we increase the radius ratio either by increasing the size of the cation or by decreasing the size of the anion, the structure will become unstable. All the anions will no longer be touching one another. If the radius ratio is further increased, the anions will be going farther and farther apart. Consequently, a stage may reach when more number of anions may be able to fit around the cation, giving more stable structure. In other words, there may be change in coordination number from 6 to 8. This means that there is a upper and lower limiting radius ratio for which the coordination number 6 is stable. It has been calculated that the octahedral coordination number 6 is stable for the radius ratio in the range of 0.414 to 0.732. That is, if the radius ratio is in the range, only then the cation will be able to keep 6 anions in contact with it. If the R positive divided by R negative ratio is less than 0.414, the coordination number will decrease to 4, and if the radius ratio is more than 0.732, the coordination number will increase. Similarly, for the radius ratio ranging between 0.225 to 0.415, tetrahedral site will be preferred in which the coordination number of cation is 4. For the radius ratio ranging between 0.155 to 0.225, trigonal site will be preferred in which the coordination number of cation will be 3. On the higher side of octahedral site, if the radius ratio is above 0.732 cubic site, coordination number 8 will be formed. Thus, we find the radius ratio is a very important factor in determining most stable type of arrangement of ions in the crystal lattice of an ionic solid. The permitted coordination numbers and structural arrangement of anions around the cations are different R positive upon R negative ratios as given in table. The radius ratio between 0.155 to 0.225, its coordination number permitted is 3 and the structural arrangement will be plane triangular. For example, boron oxide. Now the radius ratio, if it is between 0.225 to 0.414, then the permitted coordination number in this is 4 and the structural arrangement is tetrahedral. For example, zinc blende. If the radius ratio is between 0.414 to 0.732, then the permitted coordination number is 6 and the structural arrangement is octahedral, for example NaCl. Last, if the radius ratio lies between 0.732 to 1.00, then the permitted coordination number is 8 and the structural arrangement is cubic, for example cesium chloride. Now, the application of radius ratio rule may be illustrated by the following examples. First, the radius of Na positive ion is 0.95 angstrom and that of chloride ion is 1.81 angstrom. Hence, the radius ratio R Na positive divided by RCl negative is equals to 0.95 divided by 1.81, that is equals to 0.524. The ratio lies between 0.414 and 0.732. Hence, Na positive ions prefers to occupy octahedral sites having coordination number 6 in the close packed lattice of chloride ions. Second, the radii of Zn2 positive and S2 negative ions are 0.74 angstrom and 1.84 angstrom respectively, so that the radius ratio Rzn2 positive divided by Rs2 negative is equals to 0.74 divided by 1.84, which is equals to 0.40. This radius ratio lies between 0.225 and 0.414 and therefore the Zn2 positive ions prefer to occupy tetrahedral holes having coordination number 4 in close packed lattice of S2 negative ions. Thirdly, the radii of Rb positive and I negative ions are 1.47 angstrom and 2.16 angstroms respectively. The radius ratio is Rb positive divided by Ri negative is equals to 1.47 divided by 2.16, that is equals to 0.68. The radius ratio lies between 0.414 to 0.732 and therefore Rb positive prefer to occupy octahedral holes having coordination number 6 in close packed arrangement of I negative ions. Now next topic is limitations of radius ratio rule. Although radius ratio rule is useful concept for predicting and understanding the structure of ionic compounds, yet it is not perfect. It has many limitations also. So some of the common limitations of radius ratio rule are: first, the radius ratio rule applies only to the packing of hard spheres of known size. This is far from reality. Anions are not hard but are polarizable under the influence of cations. The extent of polarization of anions lead to covalency and result in serious errors in the application of radius ratio rule. For example, the radius ratio Rag positive divided by Ri negative for Agi is 0.52. Rag positive divided by I negative is equals to 1.12 divided by 2.16, that is equals to 0.52. This indicates coordination number of 6 NaCl structure, but actually AgI is 4 coordinated tetrahedral lattice and zinc blend structure. Similarly, CDS, HGS and ZNO have radius ratio values greater than 0.5 but have tetrahedral structure. Second limitation, many serious errors occur for the coordination number 6 versus 8. Coordination number 8 is found only in cesium chloride, cesium bromide and cesium iodide. Although radius ratio calculation predicts cesium chloride coordination number to be 8, structures for oxides of larger divalent metal ions such as Ba2 positive, Sr2 positive and Pb2 positive, yet no 8 coordinate oxide MO has been observed. Third limitation is that radius ratio rule fails to explain why some compounds crystallize in more than one modifications having different coordination numbers. For example, thallium chloride crystallizes in two forms adopting NaCl structure having coordination number 6 with internuclear distance 3.15 angstrom, and cesium chloride structure having coordination number 8 internuclear distance 3.32 angstrom. Fourth limitation is that effective radius of a cation is greatly influenced by the anions, so that radius ratio changes. For example, AgF and NaF crystallize out in NaCl type structure with coordination number 6, and if we assume that size of fluoride ions remain constant, then Ag positive is bigger than Na positive. On the other hand, for a given size of chloride ion in AgCl and NaCl, the size of cations are reversed, that is, Na positive is bigger than Ag positive ion. Internuclear distance in angstrom is for AgF is 2.47, NaF 2.31, AgCl 2.77, NaCl 2.82. It is also true for their bromides. This is understable because Ag positive ion is softer than Na positive and introduce relatively more covalent character with polarizable anions like Cl negative and Br negative ions. These changes in size of cations may introduce errors in the radius ratio rule calculations and predictions. Thus, radius ratio rule calculations are very useful for predicting coordination number of ionic or partially ionic compounds, but such predictions can be misleading when atomic and ionic radii are not well defined. Now, next topic is calculation of radius ratios. We have learned that the stable ionic lattice have commonly four types of interstitial sites, namely trigonal, tetrahedral, octahedral and cubic, corresponding to coordination number 3, 4, 6 and 8 respectively. In general, the size of trigonal site is smaller than the size of tetrahedral sites, which in turn is smaller than the size of octahedral site. The size of octahedral site is smaller than that of a cubic site. The size of a site varies with the size of the spheres surrounding it. The radius of a small sphere cation, which can perfectly occupy a given site created by a large sphere anion, can be calculated by simple geometry. These are generally calculated in terms of the ratio of the radius of cation to that of anion, as given below. First is radius ratio for trigonal site. A trigonal site is formed when the three spheres lie at the vertices of an equilateral triangle as shown. Let R positive and R negative be the radii of the cation and anion respectively in an equilateral triangle DBC, where BC is equals to CD, which is equals to BD, that is equals to 2R negative. If A is the center of the triangle and hence of the cation, then thus BE is equals to R negative and AB is equals to R positive plus R negative. Since triangle EBA is a right angle triangle, hence cos angle ABE is equals to BE upon AB, that is cos 30 degree will be equal to R negative divided by R negative plus R positive. Since cos 30 degree is equals to root 3 by 2, root 3 by 2 is equals to R negative divided by R negative plus R positive. On inverting both sides, 2 by root 3 is equals to r negative plus r positive divided by r negative, which is equals to 1 plus r positive divided by r negative. Thus, r positive divided by r negative is equals to 2 by root 3 minus 1. That is equals to 2 minus 1.732 divided by 1.732, which is equals to 0.268 divided by 1.732, that is equals to 0.155. Thus, the limiting r positive by r negative ratio for trigonal site is 0.155. Thus, for cations to occupy a trigonal site of the anions, the r positive divided by r negative should not be smaller than 0.155. Only B3 positive ions can fit in such a small type in its oxide B2O3. Second is radius ratio for tetrahedral site. A tetrahedral site in a cube is shown by placing spheres at the alternate cones as shown in figure. A stable tetrahedral arrangement has 4 anions at the corners touching each other and also the cation placed at the center. However, for simplicity, the cations and anions are shown by distinct circles. Actually, the cations and anions are touching one another. Suppose the anions are present at the alternate corners of a cube and the cation occupies the tetrahedral site. Suppose A is the length of each side of the cube and R positive and R negative are the radii of the cation and anion respectively. In the figure, AC is a face diagonal in triangle ABC, where AC square is equals to AB square plus BC square, or we can say that AC is equals to under root AB square plus BC square. So under root A square plus A square is equals to root 2A. The two anions at the face diagonal, those shown by distinct circles, are actually touching each other, so that AC is equals to R negative plus R negative, that is equals to 2R negative. 2R negative is equals to under root 2A. R negative is equals to under root 2A divided by 2, that is equals to A by root 2. AD is the body diagonal in triangle ADC, where AD square is equals to AC square plus CD square. AD will be equal to under root AC square plus CD square. So, we can say that AD is equals to under root 2A ka whole square plus A square, that will be equal to under root 3A. The cation is present at the center of the body diagonal AD, so that half of the length of this diagonal is equal to the sum of the radii of the cation and the anion. Thus, R negative plus R positive will be equal to AD divided by 2, that will be equal to under root 3 multiply A divided by 2. Dividing equation 3 by 1, we get R negative plus R positive divided by R negative, that will be equal to under root 3A divided by 2 multiply root 2 divided by A, that will be equal to under root 3 by under root 2. Or we can say that R positive by R negative will be equal to under root 3 by under root 2 minus 1, that will be equal to under root 3 minus under root 2 divided by under root 2. That will be equal to 1.732 minus 1.414 divided by 1.414. That will be equal to 0.225. Thus, the limiting R positive by R negative ratio for tetrahedral site is 0.225. Third is radius ratio for octahedral site. A cross section through an octahedral site shows that the 4 anions are at the corners of a square and the cations is at the center. 1 anion each at the top and the bottom of the plane formed by 4 anions also touch the cation. ABCD is a square. Suppose each side of the square is A and R positive and R negative are the radii of cation and anion respectively. In right angle triangle ABC, AC square is equals to AB square plus BC square, or AC is equals to under root AB square plus BC square, that is equals to under root A square plus A square, which will be equal to under root 2A. But it is evident from the figure that AC is equals to R negative plus 2R positive plus R negative. That will be equal to 2R negative plus 2R positive. So 2R negative plus 2R positive will be equal to under root 2A, or we can say that R negative plus R positive will be equal to under root 2A divided by 2. This is equation first. It is clear from the figure AB is equals to A, that is equals to 2R negative. R negative is equals to A by 2. This is equation second. Now dividing equation 1 by 2, we get R negative plus R positive divided by R negative, that will be equal to under root 2A divided by 2 multiply 2 divided by A, that is equals to under root 2. Or we can say that R positive divided by R negative is equals to under root 2 minus 1, which is equals to 1.414 minus 1, which will be equal to 0.414. Thus the limiting radii ratio of octahedral site is 0.414. Thus the cations to occupy a octahedral site of anions, the R positive divided by R negative should not be less than 0.414. Now the fourth is radius ratio of cubic site. The spheres are not shown touching one another for the sake of our simplicity. Suppose the length of each side of the cube is A and R positive and R negative are the radii of cation and anion respectively. In the figure, AB is equals to 2R negative, that is equals to A, or we can say that R negative is equals to A divided by 2. AC is a face diagonal in triangle ABC. AC square is equals to AB square plus BC square, or we can say that AC is equals to under root AB square plus BC square, that is equals to under root A square plus A square, which is equals to under root 2A. AD is a body diagonal in triangle ACD. AD square is equals to AC square plus CD square, or we can say that AD is equals to AC under root AC square plus CD square. Now under root bracket starts under root 2A whole square plus A square is equals to under root 3A. As evident from the figure, the body diagonal AD is equals to R negative plus 2R positive plus R negative, that is equals to 2R negative plus 2R positive. Therefore 2R negative plus 2R positive will be equal to under root 3A. Or we can say that R negative plus R positive is equals to root 3A by 2. Now dividing equation 2 by 1, we get R negative plus R positive divided by R negative, that is equals to under root 3 by 2 A multiply 2 by A, that is equals to under root 3. Or we can say that R positive divided by R negative is equals to under root 3 minus 1, which is equals to 1.732 minus 1 is equals to 0.732. Thus the limiting radii ratio for cubic site is 0.732. Thus for cations to fit into the cubic site of anions, the radii ratio should not be less than 0.732. Okay, now next topic is lattice defects. Ionic crystals have well-defined order of the constituent ions, and ionic crystals which has the same unit cell containing the same lattice points throughout the whole of the crystal is known as ideal crystal. However, such ideal crystal exist only at absolute 0 Kelvin temperature. At any temperature above 0 Kelvin, the crystals have same departure from complete ordered arrangement. Any deviation from completely ordered arrangement in a crystal constitutes a disorder or a defect. The crystal may have additional defects due to the presence of some impurities. The term disorder or imperfection is generally used to denote departure from perfectly ordered state of the constituent of the crystals. These imperfections will not only change the properties of the crystals but also give rise to new properties. There are commonly two types of defects in crystals. A. Defects in stoichiometric crystals. Second, defects in non-stoichiometric crystals. Now A. Defect in stoichiometric crystals. Stoichiometric compounds are those in which the number of positive and negative ions are exactly in the ratio indicated by their chemical formulae. For simplicity, we can consider the compounds of the type AB having equal number of A positive and B negative ions. The defect in these types of compounds are known as stoichiometric defects. In these compounds, two types of defects are generally observed. These are Schottky defect and Frankel defect. First, what is Schottky defect? This defect was discovered by German scientist Schottky in 1930. It arises if some of the atoms or ions are missing from their normal lattice sites. The lattice sites which are unoccupied are called lattice vacancies or holes. Since the crystals is to remain electrically neutral, equal number of cations and anions are missing. The ideal AB crystal is shown in figure. The existence of two holes, one due to a missing cation and other due to missing anion, is shown in figure. Conditions causing Schottky defects. This type of defect is usually observed in strongly ionic compound having high coordination number and ions, cations and anions of almost similar sizes. For example, NaCl, KCl, KBr and CaCl ionic solids have Schottky defects. It has been observed that in NaCl there are about 10 to the power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube there are about 10 to the power 22 ions, and this means that there will be one Schottky defect per 10 to the power 16 ions in NaCl. Because of the presence of a large number of vacancies in crystals, its density is markedly lowered. Second is Frenkel defect. This defect was discovered by a Russian scientist Frenkel in 1926. It arises when an ion is missing from its normal position and occupies an interstitial site between the lattice points. The existence of one hole due to a missing cation from its normal position and occupying an interstitial position is shown in figure. In this case, only the crystal remains electrically neutral because the number of anions and cation remains the same. Conditions causing Frenkel defects. This defect generally occurs in compounds which have coordination number low and anions are much larger in size than the cations. In pure alkali metal halides, these defects are not very common because the ions cannot get into the interstitial positions due to their large sizes. These defects can be found in silver halides such as AgCl, AgBr, AgI, etc. Because of small size of Ag positive ion, it cannot go into the interstitial sites. We observe that vacancies or holes are present in crystals with Schottky as well as Frenkel defect, but the former leads to decrease in the overall density of the substance, but the latter does not. In certain ionic solids such as AgBr, both Schottky and Frenkel defects occur. Now, consequences of Schottky and Frenkel defects. Schottky and Frenkel defects in crystals lead to some interesting consequences. These are given below. First, because of the presence of these defects, the electrical conductivity of crystal increases. When an electric field is applied, a nearby ion moves from its lattice site to occupy a hole. This results in creating a new hole and other nearby ion moves into it, and so on. This process continues and a hole thereby moves from one end to the another end. Thus it conducts in electricity across the whole of the crystal. Second, due to the presence of holes in the crystals, its density decreases. However, it may be noted that density decreases only for crystals having Schottky defects. Thirdly, the presence of holes also decreases the lattice energy or the stability of the crystal. The presence of too many holes may cause a partial collapse of the lattice. Fourth, the closeness of similar charges in Frenkel defects tend to increase the dielectric constant of the crystals. Now next is difference between Schottky and Frenkel defects. Schottky defect. Firstly, it is produced because of missing atoms or ions from their normal crystal sites. In Frenkel defect, it is produced when some atoms or ions are displaced from their normal sites and occupy interstitial sites. Secondly, in Schottky defect, the presence of Schottky defect lowers the density of the crystal, and in Frenkel defect, the density of the crystal is not affected. Thirdly, it is generally shown by ionic solids having high coordination number and in which the cations and anions are of equal sizes, example NaCl and cesium fluoride. In Frenkel defect, it is generally exhibited by ionic solids having low coordination number and in which anions are larger in size than the cations, example AgCl and ZnS. Now next topic is defect in non-stoichiometric crystals. The compounds in which the ratio of positive and negative ions present in the compound differs from that required by the ideal chemical formula of the compound are called non-stoichiometric compounds. The defects in these compounds are called non-stoichiometric defects. Vanadium oxide, for example, has the formula VOX, where X lies between 0.6 and 1.3. Similarly, iron 2 oxide sample contains more oxygen atoms than iron atoms, while sample of zinc oxide usually has excess of zinc atoms than oxygen atoms. However, it may be noted in each case the electrical neutrality of the crystal is maintained. These are of two types depending upon whether positive ions are in excess or negative ions are in excess. These are also known as metal excess defects and metal deficiency defects respectively. Some of these examples are given below. Now first is metal excess defect. In these defects, the positive ions are in excess. These may arise due to following two ways. First is anion vacancies. In this case, negative ions may be missing from their latest sites, leaving holes in which the electrons remain entrapped to maintain the electrical neutrality. Evidently, there is an excess of positive ions, although the crystal as a whole is electrically neutral. This type of defect is observed in those crystals which are likely to form Schottky defects. For example, in alkali metal halides, anion vacancies are produced when alkali metal halide crystals are heated in the atmosphere of the alkali metal vapors. The metal atom get deposited on the surface of the alkali metal halide crystal. Halide ions move into the surface and combine with metal atoms. The electrons thus produced by the ionization of the metal atoms diffuse into the crystal and get trapped at the anion vacancies. The electrons trapped in anion vacancies are referred to as F centers. These give very interesting properties. For example, the excess of potassium in KCl makes the crystal appear violet. Excess of lithium in LiCl makes the crystal appear pink. Second is excess cation occupying interstitial sites. In this case, there are extra positive ions occupying interstitial sites and the electrons in another interstitial sites to maintain electrical neutrality. The defect may be visualized as the loss of non-metal atoms which leave their electrons behind. The excess metal ions occupy interstitial position. This type of defect is found in crystals which are likely to develop Frankel defect. The common example is zinc oxide. ZnO loses oxygen reversibly at high temperature and turns yellow in color. The excess Zn2 positive ions are trapped in interstitial sites and equal number of electrons are trapped in the neighborhood to balance the electrical charge. These electrons give rise to the enhanced electrical conductivity. Now next topic is consequences of metal excess defect. First, the crystals with metal excess defects conduct electricity due to presence of free electrons. However, the conductivity is very low because of the number of defects and therefore the number of free electrons is very small. Because of low conductivity as compared to conductivity of metals, these are called semiconductors. These compounds are also called n-type semiconductors since current is carried by the electrons in the normal way. Second is the crystals with metal excess defects are generally colored. For example, non-stoichiometric sodium chloride is yellow, non-stoichiometric potassium chloride is violet. Second is metal deficient defects. These contains less number of positive ions than negative ions. These arise due to two ways. First is cation vacancies. In some cases, the positive ions may be missing from their latest sites. The extra negative charge may be balanced by some nearby metal ion acquiring two positive charge instead of one. This type of defect is possible in metals which show variable oxidation states. The common example of compounds having this defect are ferrous oxide, ferrous sulfide, nickel oxide, etc. In case of iron pyrites, that is FeS, for example, 2 out of 3 ferrous ions in a lattice may be converted into Fe3 positive state and the third Fe2 positive ion may be missing from their lattice site. Therefore, the crystal contains Fe2 positive and Fe3 positive ions. This gives rise to exchange of electrons from one Fe2 positive ion to Fe3 positive ion in which Fe2 positive ion changes to Fe3 positive and Fe3 positive changes to Fe2 positive ion. As a result, the crystal has metallic luster because of the natural color of iron pyrites and metal luster. Some samples of minerals shine like gold and have been nicknamed as fool's gold. Moreover, since there is exchange of electrons, the substance become conductors. Third is excess anions occupying interstitial sites. In this case, the extra anions may be occupying interstitial positions. The extra negative charge is balanced by the extra charge oxidation of equal number of cations to higher oxidation states on the adjacent metal ion. This such type of defect is not common because the negative ions are usually very large and they cannot easily fit into the interstitial sites. Now, what are the consequences of metal deficient defects? Crystal with metal deficient defects are semiconductors. The conductivity is due to the movement of electrons from one ion to another. For example, when an electron moves from ion A positive, it changes to A2 positive. It is called movement of positive hole and the substances are called p-type semiconductors. The conductivity of semiconductor is mainly due to the presence of impurities and defects. The semiconductors are very important solid state materials having many important applications in electronics. Semiconductors are important class of compounds which have higher conductivity than insulators and have much lower conductivity than conductors. These are discussed in detail in Unit 5. Now next topic is lattice energy of ionic crystals. The stability of ionic crystals is determined in terms of their lattice energy. Lattice energy is defined as the amount of energy released when 1 mole of ionic crystal is formed from its constituent ions in the gaseous state. The formation of 1 mole of the ionic solid from its constituent gaseous ions may be represented as M positive, which is in gaseous state, plus X negative, which is also in gaseous state, will be equal to Mx, which will be in solid state. Here delta H is lattice energy, which is equals to minus U. The lattice energy is expressed by U. The negative sign is used because energy is released in the process. Since ionic bond is formed as a consequence of electrostatic attractions between the oppositely charged ions, there is considerable decrease of potential energy of the system. As a result, if 1 mole of solid ionic compound is broken into its constituent gaseous ions, energy will be needed which will be numerically equal to the lattice energy. Hence, Mx, which is solid in state, will be equal to M positive, which was gaseous in state, plus X negative will be gaseous in state. Here delta H will be plus U. In this case, U has positive sign because energy is absorbed in the process. It is obvious that if the compound is stable, a large amount of energy will be needed numerically equal to lattice energy. This means that the higher lattice energy of an ionic compound, the greater will be its stability. Lattice energy of some ionic compounds are given in table 3. So if we see the first is ionic solid is LiF, its lattice energy is minus 1033. Then CSF, its lattice energy is minus 748. Then NaCl minus 778, NaBr minus 752, LiI minus 140, CSI minus 601, AgCl minus 895, AgI minus 795, CaF2 minus 2581, CaCl2 minus 2254, MgF2 minus 2882, MnCl2 minus 2525, BeO minus 3125, MgO minus 3932, MgS minus 3254, and then zinc oxide minus 4032. It is evident from the above table that the lattice energy of the ionic solids are quite high. This is because of strong electrostatic attractions between oppositely charged ions present in the solid. Since Coulombic force of attraction vary directly as the product of the charges, it follows that the higher the valency charge of the ions, greater would be the lattice energy of the ionic solid. Thus, lattice energy increases as we move from univalent ionic solids to bivalent ionic solids and then to bivalent ionic solids. Now next topic is Born-Haber cycle for latest energies. Born and Haber 1919 proposed a method to relate the latest energy of an ionic crystal to the other thermodynamic data. This is known as Born-Haber cycle. We have learned that the formation of bond takes place only if there is decrease of energy. As an example, let us consider the energy changes during the formation of sodium chloride from metallic sodium and chlorine gas and the formation of a Born-Haber cycle. Na plus 1 by 2 Cl2 is equals to NaCl. The overall process is thought to make place in following steps. First, conversion of metallic sodium into gaseous sodium atoms. The sodium atom can lose its electron only in the gaseous state and has to be sublimated. The energy required for the conversion of 1 mole of metallic sodium into gaseous sodium is called sublimation energy. It is represented by capital S. Now sodium plus sublimation energy will be equal to sodium into gaseous state. Second is dissociation of chlorine molecules into chlorine atoms. Each chlorine molecule consists of two atoms of chlorine. The amount of energy required for the conversion of gaseous chlorine molecule into atoms is known as dissociation energy. It is represented by capital D. So, 1 mole of chlorine gas plus dissociation energy will be 2 chlorine in gaseous states. Thus, the energy required for producing 1 mole of gaseous chlorine atoms is D by 2. So 1 by 2 Cl2 in gaseous state plus D by 2 is equals to Cl in gaseous state. Third is conversion of gaseous sodium atoms into sodium ions. The amount of energy required to convert 1 mole of gaseous sodium atoms into sodium ions in the gaseous state is called ionization energy. It is denoted by IE. So Na plus IE is equals to Na positive plus electron. Fourth is conversion of gaseous chlorine atoms into gaseous chloride ions. The amount of energy released during the conversion of 1 mole of gaseous chlorine atoms into chloride ions is known as electron affinity, denoted by Ea. So Cl plus electron will be equal to Cl negative plus electron affinity. Fifth step is combination of oppositely charged ions to form a solid crystal. The oppositely charged Na positive and Cl negative ions attract each other to form a solid NaCl crystal. This leads to release of energy. The amount of energy released when 1 mole of solid crystalline compound is obtained from gaseous ions of the opposite charges is called lattice energy, denoted by U naught. Na positive plus Cl negative will be equal to NaCl plus U naught, where U naught is lattice energy. The overall energy change may be expressed as Na plus half Cl2 will be equal to NaCl. The heat of change of the reaction is called heat of formation and it may be denoted by delta HF. The various steps may be represented in the form of Born-Haber cycle. According to Hess laws, the heat of formation of 1 mole of sodium chloride should be the same irrespective of the fact whether it takes place directly in one step or through a number of steps as shown above. Thus, delta HF is equals to S plus half D plus ionization energy plus electron affinity plus U naught, where U naught is equals to delta HF minus S minus 1 by 2D minus ionization energy minus electron affinity. Thus, lattice energy can be calculated by knowing the values of different quantities. While using the above relation of lattice energy, a special care should be taken for the signs of various quantities. Positive sign is used for energies absorbed and negative sign is used for energies released. Now next is applications of Born-Haber cycle. The Born-Haber cycle can be used for the calculation of many properties. Some of the important uses are given below. First, calculation of heat of formation. Heat of formation of unknown compound can be easily calculated by making a Born-Haber cycle. For example, for NaCl type crystal, heat of formation is given as delta HF is equals to S plus half D plus ionization energy plus electron affinity plus U naught. Similarly, for crystals like MgF2, refer example 6, delta HF is equals to S plus D plus ionization energy plus twice electron affinity plus U naught. The heat of formation tells us about the stability of the compound. If the heat of formation comes out to be negative, that is, the reaction is exothermic, the compound formed will be stable. On the other hand, if the heat of formation comes out to be positive, that is the reaction is endothermic, the formation of the compound will be highly unfavorable energetically. From the heat of formation, it can be explained why NaCl2 is not formed, though it is expected to have higher lattice energy than NaCl. The heat of formation of NaCl2 by using Born-Haber cycle comes out to be highly positive. Now next is calculation of electron affinities. The Born-Haber cycle can be used for the calculation of electron affinities of some elements which are otherwise very difficult to measure. Heat of formation of a compound may be expressed as delta HF is equals to S plus half D plus ionization energy plus electron affinity plus U naught. It may be rearranged as electron affinity is equals to delta HF minus S minus D minus ionization energy minus U naught. In this case, H, delta F, D and ionization energy are experimentally determined, and lattice energy U naught may be calculated by using Born-Haber equation. Using the above equation, electron affinity may be calculated. Third is estimation of proton affinities. The Born-Haber cycle can also be used to calculate the proton affinities of different bases. The proton affinity of a species X is defined as the energy released in the reaction. X plus H positive is equals to HX positive. For example, the proton affinity for ammonia may be expressed as NH3 plus H positive is equals to NH4 positive. Delta H is equals to proton affinity. This can be easily calculated by considering the Born-Haber cycle. According to Born-Haber cycle, delta HF is equals to D plus ionization energy plus electron affinity plus proton affinity plus U naught. Knowing the values of delta H, F, D, IE, EA and U naught, we can easily calculate proton affinity. For reaction of NH3 and HCl, data is given. By substituting these values, we get proton affinity to be minus 891.3 kilojoule. Thus, proton affinity for ammonia is minus 891.3 kilojoule. The negative value indicates that the reaction is favorable and therefore ammonia has good tendency to accept the proton. Now next is importance of lattice energy. First, stability of ionic solids. Larger the lattice energy, greater is the stability of ionic solid. This is because larger lattice energy means stronger electrostatic attractions between the positively and negatively charged ions. As a result, more energy will be needed to break the crystalline substance, that is, the compound would be stable. Second, melting and boiling points. Salts having high lattice energies will require more energy in the form of thermal energy to break down the crystal. Consequently, melting and boiling points will be high. Third is solubilities of ionic solids. The magnitude of lattice energy of a solid gives an idea about the solubility of the substance in different solvents. Ionic compounds are generally soluble in water and other polar solvents but insoluble in non-polar solvents such as carbon tetrachloride, benzene, etc. Next topic is solvation energy and solubility of ionic solid. When an ionic solid goes into solution, the strong forces of attraction between its ions and are overcome and therefore its crystal lattice gets ruptured. But for this purpose, energy may be supplied. Now a question arises, how is this energy required to cause the rupture of the lattice? The answer is not far to seek. When an ionic solid is added to the solvent, the cations and anions present in the solid are attracted by the opposite ends of the molecules. As a result, there is a strong interaction between the solvent and the ions, resulting in the solvation of the ions. If water is the solvent and the process is called hydration of the ions. The ionic solvation or hydration is an exothermic process releasing a lot of energy. This is called solvation energy. The amount of solvation energy depends upon the nature of the solvent. If it is the energy which is utilized in causing rupture of the crystal lattice. The liquids which cause greater solvation of ions and release large solvation energy are good solvents for ionic solids. They have generally high dielectric constants. Thus, water, liquid ammonia, hydrogen fluoride, etc. are good solvents. On the other hand, liquids with low dielectric constants such as benzene, carbon tetrachloride, etc. do not solvate the ions and therefore their solvation energy is small. These are not good solvents for ionic solids. The process of ionization in water and then going in solution state has already been shown for NaCl. The water molecules act as dipoles having positive and negative ends. The positive ends of water dipoles surround the cations and anions. The amount of energy released due to this interaction, solvation energy, is sufficient to overcome the lattice energy of the crystal. Therefore, NaCl dissolves in water. In general, for a solid to dissolve in a particular solvent, its solvation energy should be greater than lattice energy of the solid. The salts of the alkaline earth metals Mg, Ca, Ba, etc. with polyvalent anions such as sulfate, oxalate, phosphate, etc. are much less soluble than the corresponding salts of alkali metals. This has been attributed to their higher lattice energies. The energy released in the solvation of the ions is not sufficiently large to break their crystal lattice to an appreciable extent. Now next is reason for low solubilities of silver halides. We know that a compound is soluble if the solvation energy is more than the lattice energy of the compound. The low solubilities of the compounds like calcium oxalate, barium sulfate, lead sulfate, etc. in water are explained on the basis of their higher lattice energies. In these cases, the lattice energy are so high that the solvation energy released is not sufficient to overcome the lattice energy. However, the low solubilities of silver halides AgCl, AgBr, AgI in water cannot be explained on the same basis. The lattice energy of these compounds are almost of the same order as those of the alkali metal halides, which are highly soluble. The unusual behavior of silver halides can be explained on the basis of the outer electronic configuration of silver. The outer electronic configuration of Ag positive is 4d10 5s0 5p0. The electronic configuration of alkali metal ions Li positive, Na positive or K positive is noble gas NS0. The d electrons screen the nuclear charge from the outer electrons less effectively than s and p electrons because of their poor penetration. See radial probability distribution curves of chapter 1. Therefore, the effective nuclear charge experienced by Ag positive ion is much more than the effective nuclear charge in the alkali metal ions. Due to greater nuclear charge, the Ag positive undergo great polarization and hence undergo appreciable charge from pure ionic character to covalent character, discussed later on Fazan rules. Therefore, silver halides are less ionic and consequently their solubility in water is low. Now next topic is covalent character in ionic compounds. Ionic and covalent bonds are two extreme theoretical types of bonds. In fact, most of heteronuclear bonds have intermediate character even in the case of pure ionic compounds. There is some degree of covalent character when two oppositely charged ions A positive and B negative are brought together. The positive ion attracts the outermost electrons of the negative ion. This results in distortion of electron cloud around the anion towards the cation. This distortion of electron cloud of the negative ion by the positive ion is called polarization. If the polarization is small, the bond is mainly ionic. On the other hand, the degree of polarization is large. Electron cloud is drawn more from the negative ion to the positive ion. Consequently, the charges on the ions become less negative because becomes less positive. Charge also becomes less because some of it is neutralized by the electron cloud of the anion. This decreases the ionic character of the bond and favors the covalent character. The polarization of the anion by cation is shown in figure. The two ions are shown without any polarization. Assuming that the bond is completely ionic, this represents an ideal on pair. The positive ion polarizes the negative ion and draws electron towards itself. As a result of polarization, there is decrease of positive charge on the cation and decrease of negative charge on the anion. This leads to the covalent character. Obviously, if polarization is more, larger will be the covalent character of the bond. Thus, the type of bond depends upon the degree of polarization. If there is no polarization, the bond is mainly ionic. If the degree of polarization is small, the bond will be ionic with some covalent character, and if the polarization is more, the covalent character becomes predominant. Now, the extent of polarization depends on both the ions as the power of the cation to distort or polarize the anion. Second, the susceptibility of the anion to get polarized by the cation. The tendency of the cation to polarize and polarizability of the anion are summarized in the following rules known as Fazan's rule. Fazan's rule. According to Fazan's rule, the polarization will be increased by following factors. First, smaller size of the cation. Smaller the size of cation, greater is its polarizing power. The polarizing power of a cation decreases with increase in its size. The small size of cations have high electron density and therefore they tend to distort or polarize the electron cloud of the anion to greater extent. This can be easily illustrated by taking example of metal chloride of group 2nd A as given in table 4. Table 4. Effect of increasing size of cation on the melting point of ionic compounds of group 2. Cation Be2 positive, radius is 0.31 and melting point 678. Mg2 positive, radius 0.65, melting point 985 Kelvin. Ca2 positive, radius is 0.99, melting point is 1045. Strontium 2 positive, radius 1.13, melting point is 1145 Kelvin. Then barium 2 positive, radius is 1.35 and melting point is 1233 Kelvin. In the table, the ionic size increases from beryllium 2 positive to barium 2 positive, same positive charge. Therefore, their polarization power decreases. As a result, the covalent character decreases or the ionic character increases. Consequently, the melting points of their halides also increase. In other words, the low melting point of BeCl2 in comparison to other alkaline earth metal halides is mainly due to its more covalent character. Second is large size of anion. The polarizability of anion increase with the increase in size of atom. This is obvious because the electron cloud on the bigger anion will be held less firmly by its nucleus and therefore would be more easily deformed towards the cation. Thus, larger the anion, higher will be its polarizability and more will be covalent character in its compound. Therefore, the anions like I negative, Br negative, S2 negative, Se2 negative, etc. are easily polarizable and have greater tendency to induce covalent character in ionic compounds. For example, for a given cation Na positive, as the size of anion increases from F negative to I negative, its covalent character increases and consequently melting point decreases. Now next is high charge on cation or anion. The polarizing power of a cation and polarizability of an anion increases with increase in charge of the ion. The highly charged cation will exert greater effect in polarizing anion and the highly charged anion will be more easily polarized. This can be easily illustrated by the following example. Na positive and Ca2 positive have almost similar ionic radii, but CaCl2 have higher covalent character than the NaCl because of higher charge on Ca2 positive. Consequently, the melting point of CaCl2 is less than that of NaCl. Fourth is electronic configuration of cation. Cation with 18 electron shell configuration known as inert or pseudo-inert configuration cause greater polarization than the cations with 8 electron shell configuration with the same size in charge. This is due to the fact that in case of 18 electron shell ion, there are 10 d electrons in addition to 8 s and p electrons. The d electrons do not shield the nuclear charge effectively and therefore they have increased effective nuclear charge. Consequently, these ions behave as though these were under the influence of great nuclear charge and distort the anions to greater extent. For example, if we compare the ions of the same size Na positive and Cu positive, Na positive has 8 electron shell configuration 2s2 2p6, while Cu positive has 18 electron shell configuration 3s2 3p6 3d10. The Cu positive ion polarizes the anion to a greater extent than Na positive ion. As a result, the copper halide CuCl is slightly covalent and therefore insoluble in water, whereas NaCl is ionic and highly soluble in water. The covalent character of CuCl comparison to NaCl is also supported by its low melting point. Now next is melting point of CuCl is 705 Kelvin and that of NaCl is 1073 Kelvin. Similarly, Ca2 positive and Hg2 positive have almost similar ionic radii, but Hg2 positive has 18 electron shell that have 4f14, 5s2, 5p2, 6d10, whereas Ca2 positive has 8 electrons shell 3s2, 3p6. Therefore, Hg2 positive is more polarizing than Ca2 positive and its compounds are more covalent. For example, melting point of HgCl2 is 549 Kelvin, while that of CaCl2 is 1065 Kelvin. We have already explained the low solubilities of silver halides in water in comparison to sodium halides. The silver halides acquiring covalent character because of great polarizing power of Ag positive ion. Thus, according to Fazan's rule, the covalent character will be favored by first, small size of cation, second, large size of anion, third, high charge of cation and anion, and fourth, the cation having 18 electrons shell. Thank you. This was the old chapter.